In March of 1979, Voyager 1 finally arrived at Jupiter. What it found there changed planetary science forever. Jupiter is the largest planet in our solar system. It is a gas giant, more than 11 times wider than Earth, with a mass greater than all the other planets combined. Even through telescopes, astronomers had already seen Jupiter's swirling cloud bands and its massive storm known as the Great Red Spot. But Voyager was about to reveal details no one had ever seen before. As the spacecraft approached Jupiter, its cameras captured incredibly detailed images of the planet's atmosphere. Enormous storms churned across the cloud tops. Jet streams wrapped around the planet at hundreds of kilometers per hour. And lightning storms flashed inside the thick atmosphere. But the biggest surprise wasn't Jupiter itself. It was one of its moons, a small moon called Io. Before Voyager arrived, scientists believed moons in the outer solar system were mostly frozen and inactive. Io proved them wrong. Voyager discovered that Io was covered in active volcanoes. Massive plumes of sulfur and volcanic gas were erupting hundreds of kilometers above the moon's surface. It was the first time active volcanism had ever been observed on another world. And it revealed that Jupiter's powerful gravity was stretching and heating Io from the inside. The result was a moon that looked more like a cosmic lava field than a frozen rock. Voyager also revealed Jupiter's enormous magnetosphere. This magnetic field traps high-energy particles and creates one of the most intense radiation environments in the solar system. The magnetosphere extends millions of kilometers into space, forming a vast magnetic bubble around the planet. These discoveries showed scientists that the outer solar system was far more dynamic and complex than anyone had expected. But Voyager's journey wasn't over. After its close encounter with Jupiter, the spacecraft used the planet's gravity to slingshot itself even farther into the outer solar system. Its next destination was another giant world, the ringed planet Saturn. After leaving Jupiter, Voyager 1 continued its journey toward another giant planet, Saturn. Saturn is the second largest planet in the solar system and one of the most recognizable objects in space because of its spectacular rings. These rings are made of billions of pieces of ice and rock, ranging in size from tiny grains to chunks larger than mountains. From Earth, Saturn's rings appear as a thin band of light. But as Voyager approached the planet in 1980, the spacecraft revealed something astonishing. The rings were far more complex than scientists had imagined. Instead of a few simple bands, the rings were divided into thousands of individual ringlets, separated by narrow gaps and gravitational patterns. Some of these gaps were created by the gravity of Saturn's moons. Others were caused by intricate orbital interactions within the rings themselves. Voyager also discovered new moons orbiting Saturn. But the most important target of the flyby was a moon called Titan. Titan is the largest moon of Saturn and the second largest moon in the entire solar system. Even before Voyager arrived, scientists knew Titan was unusual. It is the only moon in the solar system with a thick atmosphere. This atmosphere is rich in nitrogen and contains complex organic molecules. Because of this, some scientists believed Titan might hold clues to the chemical processes that once occurred on early Earth. To study Titan more closely, Voyager 1 performed a carefully planned flyby. The spacecraft passed within about 6,500 kilometers of Titan's surface. However, this maneuver had a consequence. The trajectory needed to reach Titan meant Voyager 1 could no longer continue toward Uranus and Neptune like its sister spacecraft, Voyager 2. Instead, the Titan flyby changed Voyager 1's path forever. The spacecraft was now heading upward, out of the plane of the solar system. Its planetary tour was over, but a new mission was beginning. Voyager 1 was now on a path that would eventually carry it beyond the outer planets and toward the edge of the Sun's influence. After the Saturn flyby in 1980, Voyager 1's primary mission was complete. The spacecraft had successfully explored Jupiter and Saturn, sending back thousands of images and scientific measurements. By any measure, the Voyager mission was already a historic success. But Voyager itself was still healthy. Its instruments were working. Its communication system was still functioning, and it still had power. So instead of shutting the spacecraft down, NASA made a bold decision. Let Voyager keep going, far beyond the planets, far beyond the region of space humans had ever explored. As Voyager traveled outward, it entered a vast and mysterious region known as the outer heliosphere. To understand this region, we first need to understand something called the solar wind. The sun constantly releases a stream of charged particles that flows outward in all directions. This stream of particles carries the sun's magnetic field with it. Together, the solar wind creates a massive bubble around our solar system. This bubble is called the heliosphere. Inside the heliosphere, space is dominated by the sun. Its magnetic field, its particles, and its influence shape the environment around every planet. But the heliosphere does not extend forever. Eventually, the outward pressure of the solar wind meets the pressure of the surrounding galaxy. At that boundary, the influence of our sun begins to fade. Scientists call this boundary the heliopause. For decades, researchers could only estimate where this boundary might exist. No spacecraft had ever reached it. But Voyager 1 was now traveling toward that frontier. Every year, the spacecraft moved farther from the sun, billions of kilometers deeper into the outer solar system. And slowly, Voyager began approaching one of the most important boundaries in space exploration. The place where the sun's influence ends and true interstellar space begins. For more than 3 decades, Voyager 1 continued its silent journey away from the sun. Every year, it traveled billions of kilometers farther into the darkness beyond the planets. As the spacecraft moved outward, its instruments began detecting subtle changes in the space environment. The solar wind was weakening. Cosmic radiation from outside the solar system was increasing. These changes suggested Voyager was approaching the boundary between our solar system and the wider galaxy. Scientists call this boundary the heliopause. It marks the point where the outward pressure of the sun's solar wind is finally balanced by the pressure of the interstellar medium, the thin gas and particles that fill the space between stars. For decades, researchers debated exactly where this boundary might be. Some believed it was closer. Others thought it might be much farther away. Then, in August of 2012, something remarkable happened. Voyager's instruments recorded a sudden and dramatic change. The number of charged particles from the sun dropped sharply. At the same time, high-energy cosmic rays from deep space surged dramatically. Another instrument detected an increase in plasma density, indicating Voyager had entered a region filled with particles from outside our solar system. Together, these measurements told a clear story. Voyager 1 had crossed the heliopause. It had officially entered interstellar space. For the first time in human history, a spacecraft built on Earth was directly sampling the environment between the stars. But the moment was strangely quiet. There was no bright line in space, no dramatic visual boundary, just a gradual shift in invisible particles and magnetic fields. Yet scientifically, it was one of the most important milestones in space exploration. Humanity had reached beyond the sun's protective bubble, and Voyager 1 was now traveling through the vast interstellar medium of our galaxy. But this incredible achievement raised another question. If Voyager is now billions of kilometers away in interstellar space, how are we still communicating with it at all? One of the biggest mysteries about Voyager 1 is simple. How does the spacecraft still have power after nearly half a century in space? Most spacecraft rely on solar panels, but far from the sun, sunlight becomes extremely weak. By the time you reach the orbit of Jupiter, sunlight is already about 25 times weaker than it is at Earth. Beyond Saturn, solar panels would produce almost no useful electricity. Voyager needed a different kind of power source. Instead of solar energy, the spacecraft runs on something called a radioisotope thermoelectric generator, or RTG. RTGs are essentially nuclear batteries. Inside each RTG is a small amount of a radioactive material called plutonium-238. Plutonium-238 naturally decays over time. As it decays, it releases heat. That heat is then converted directly into electricity using devices called thermoelectric converters. The process has no moving parts, no combustion, no mechanical engines, just heat flowing through special materials that generate electric current. This design is extremely reliable. That reliability is why RTGs have powered many deep space missions, including the Voyager spacecraft, the Cassini mission to Saturn, and NASA's Mars rovers. When Voyager launched in 1977, its RTGs produced about 470 watts of electrical power. That's roughly the same as a small household appliance. But as the plutonium slowly decays, the power output gradually decreases. Every year, Voyager has a little less electricity available. To keep the mission alive, engineers have carefully turned off non-essential systems over time. Some instruments were shut down decades ago. Others were powered off more recently to conserve energy. This careful power management is the reason Voyager is still operating today. But even with a nuclear power source, electricity alone isn't enough. The spacecraft still needs to do something incredibly difficult. It has to send a radio signal across billions of miles of space, and somehow, Earth is still able to hear it. Even with power, Voyager still faces another enormous challenge: communication. The spacecraft is now more than 24 billion kilometers from Earth. At that distance, any radio signal it sends becomes incredibly weak. By the time Voyager's transmission reaches our planet, the signal is weaker than the energy of a falling snowflake hitting the ground. Yet somehow, we can still hear it. The reason is a global communication system called NASA's Deep Space Network, often shortened to DSN. The Deep Space Network is made up of massive radio antennas located in 3 places around the world. One complex is in California's Mojave Desert, another is near Madrid, Spain, and the third is located near Canberra, Australia. These 3 locations are spaced around the planet so that as Earth rotates, at least one antenna can always point toward distant spacecraft. Some of these antennas are enormous. The largest dishes are 70 meters wide, about the height of a 20-story building. Their size allows them to collect extremely faint radio signals from deep space. When Voyager sends data, the spacecraft uses its high-gain antenna, a large dish designed to focus radio waves into a narrow beam aimed toward Earth. Even then, the signal arriving at Earth is unimaginably weak. To detect it, the Deep Space Network uses extremely sensitive receivers and advanced signal processing computers. These systems filter out background noise and amplify the tiny signal coming from Voyager. The result is a steady stream of scientific data traveling across billions of kilometers of empty space. This communication link allows scientists to monitor Voyager's instruments, send commands, and receive measurements from interstellar space. It is one of the longest distance communication systems ever operated by humanity. But the Voyager mission is slowly approaching its final chapter, because even nuclear power sources don't last forever. And one day, the spacecraft's signal will finally fade into silence. Even today, Voyager 1 continues its journey into the darkness between the stars. It is traveling at more than 17 kilometers per second. Every year it moves farther from the sun and deeper into interstellar space, but eventually the spacecraft will fall silent. The radioisotope power generators that provide Voyager's electricity slowly lose strength over time. Engineers expect that sometime in the 2030s, there will no longer be enough power to operate the spacecraft's instruments. One by one, the systems will shut down. Eventually, Voyager will no longer be able to aim its antenna toward Earth. And when that happens, the signal we've been receiving for nearly half a century will disappear. Not because the spacecraft has stopped moving, but because it no longer has the power to speak. Even then, Voyager's journey will continue. Long after its instruments go silent, the spacecraft will keep drifting through the galaxy. For thousands, even millions of years, Voyager carries something remarkable with it. Attached to the side of the spacecraft is a gold-plated copper disc known as the Voyager Golden Record. Created by a team led by astronomer Carl Sagan, the record contains sounds and images from Earth, greetings in multiple languages, music from different cultures, and recordings of natural sounds from our planet, ocean waves, birdsong, wind. It is a message placed aboard the spacecraft in case another civilization ever encounters it in the distant future. The chances of that happening are extremely small. Space is unimaginably vast, but the Golden Record was never really about being found. It was about leaving a trace of who we were, a small piece of humanity traveling among the stars. And so Voyager continues its silent voyage. A machine built in the 1970s, still moving through the galaxy, still carrying the curiosity of the species that created it. And if you ever look up at the night sky, somewhere out there, far beyond the planets, a tiny spacecraft is still traveling outward, carrying a message from Earth.